Have you ever dove straight down into the deep end of a swimming pool? As you reach the bottom, you feel that familiar squeeze. But then you grab a friend, push off the floor, and realize you can lift them with a single hand, like you have super strength. This is the same reason why thousands of tons of solid steel can rest on the surface of the ocean without sinking. To understand how this works, we have to look at how water behaves. If you put a heavy box on a table, it only presses straight down. But liquids are different. Because their molecules are constantly moving and sliding, they press inward from every possible direction at once. This creates a strange contradiction. If water is constantly squeezing you from all sides, why do you feel lighter in the pool, instead of just feeling crushed? It all comes down to how fluids distribute a push. When water is held in a container, any pressure you apply to it doesn't just stay in one spot. It travels through the entire liquid in every direction. Imagine a plastic bottle with tiny holes poked around the base. If you cap it and squeeze the top, water doesn't just trickle out. It squirts out of every single hole with the exact same force. This means that whenever you're underwater, the fluid is pushing straight against every surface it touches. It's a constant perpendicular push on every single inch of your skin. Because this push is happening on every side of an object, it sets the stage for a physical tug-of-war where one side has a massive advantage. Let's visualize this with a simple square block sitting underwater. The fluid is pressing against all four sides of this block at the same time. Since the left and right sides of the block are at the exact same depth, the water pushes against them with the same intensity. These two horizontal pushes perfectly match and cancel each other out. But remember how your ears pop at the bottom of a pool? The deeper you go, the more the water pressure grows because of the weight of the water stacked above you. This means the bottom of the block is being pushed upward much harder than the top is being pushed downward. Looking at those arrows, the result is clear. The upward push on the bottom is stronger than the downward push on the top. When we subtract that smaller downward push, we're left with a single net upper force, the buoyant force. This vertical difference is the only reason the buoyant force exists. The water is quite literally trying to lift the object toward the surface. An ancient Greek mathematician named Archimedes was the first to realize we could measure the exact strength of this invisible upward push. He saw that whenever you drop something into water, it has to push some of that water out of the way to make room for itself. We call this displaced water. Archimedes discovered that the lifting power of the buoyant force is exactly equal to the physical weight of the water that the object pushed aside. This means floating isn't some mystery. It's a physical calculation dictated entirely by how much water you can push out of the way. You can think of every submerged object as being caught in a tug-of-war. Gravity pulls the object down with its weight, while the buoyant force pushes it up. If an object is very dense, like a stone, it is very heavy for its size. Its weight overpowers the upward push of the water, and gravity wins the tug-of-war, dragging it to the bottom. But if an object is less dense than water, the buoyant force wins. It pushes the object up until it reaches the surface and finds a spot where the two forces perfectly balance. This balance point is what determines how much of an object stays underwater. To float, you simply have to push aside enough water to match your own weight. We see this clearly with icebergs. Because ice is roughly 90% as dense as seawater, an iceberg has to keep 90% of its body hidden underwater just to push aside enough water to stay afloat. Submarines use this rule to move. They can take in or pump out water to change their weight on the fly, allowing them to choose whether to win or lose that tug-of-war with the water. When you lift your friend in a swimming pool, they haven't actually lost weight. You're just getting a massive assist from the upward push of the water they've displaced. Understanding this invisible squeeze turns the magic of the swimming pool into the engineering power to navigate the globe. If you want to see more of the physics that shape our daily lives, hit the subscribe button and let us know what you want to explore next.